Recurring integrals, cyclic integration. Okay, so let's move on to a new, slightly more challenging type of integral. As you know, in the sections we've covered so far, we've been mastering integration by parts, a technique to break down complex integrals into simpler ones. Now imagine you're working on an integral, diligently applying integration by parts, expecting it to become easier with each step. But what if, instead of simplifying, the process just loops back on itself? What if, after differentiating and integrating, you find yourself right back where you started, with the original integral staring back at you? That's exactly what happens with what we call recurring integrals, sometimes also referred to as cyclic integrals. These are integrals where the repeated application of integration by parts doesn't lead to a solution directly, but instead creates a cycle. Don't worry if this sounds a bit strange right now. We'll be working through examples to make it crystal clear. In the upcoming slides, we'll learn a clever trick to handle these integrals. We won't try to solve them directly, but rather treat the integral itself as an algebraic variable, allowing us to break the cycle and find the solution. So, get ready to think a little differently about integration. Understanding the concept. Okay, so let's delve a little deeper into what recurring integrals actually are. As we discussed on the previous slide, sometimes when we use integration by parts, we don't get a simpler integral right away. This slide explains how and why that happens. First point, a recurring integral is one where, after you apply the integration by parts formula, maybe once, maybe twice, you find that the original integral you were trying to solve shows up again on the right-hand side of your equation. It's like you've gone in a circle. Now, this doesn't happen randomly. The second point tells us when we're likely to encounter these. It usually occurs when the function you're integrating, what we call the integrand, is a product of functions that, when you take their derivatives, eventually lead back to something similar to the original function. The most common example of this is when you have an exponential function, like e to the power of x, multiplied by a trigonometric function, like sine of x or cosine of x. Remember, e to the power of x remains largely unchanged when differentiated, and the derivatives of sine and cosine cycle between each other. Because the original integral keeps reappearing, the third point highlights that we can't just keep applying integration by parts indefinitely. We wouldn't get any closer to a solution, we'd just be going around in circles. That leads us to the key strategy, explained in the final point. Instead of trying to integrate further, we treat the original integral itself as if it were a simple algebraic variable. Usually we call it I. This allows us to set up an equation and solve for I algebraically, just like you would solve for x or y in an algebra problem. We'll see exactly how this works in the following slides with a detailed example, but this is the core idea behind tackling these types of integrals. The step-by-step strategy. Okay, so let's move on to slide 3. This slide outlines the step-by-step strategy we'll use to tackle these recurring integrals, or cyclic integrals, as we discussed in the previous slides. Remember, these are integrals where applying integration by parts seems to bring us back to where we started, creating a loop. We're not going to get stuck in that loop. We're going to use that looping behavior to our advantage. Step 1, assign a variable. The first thing we do is give the original integral a name, a variable. This is incredibly helpful because it allows us to treat the integral algebraically. We usually denote this variable as I. So, if our integral is the integral of e to the power of x times sine x with respect to x, we simply write I equals the integral of e to the power of x times sine x dx. This might seem trivial, but it's a crucial first step. Step 2, first application of integration by disparts. Now, we apply the integration by parts formula. You should be very comfortable with this formula by now. It states that the integral of u times v with respect to x is equal to u times the integral of v with respect to x, minus the integral of u prime, that's the derivative of u times the integral of v with respect to x, dx. The key here is to carefully choose which part of your integrand will be u and which will be v. The choice isn't always obvious, and a good choice can significantly simplify the process. Step 3, second application of integration by parts. After the first application, the resulting integral will often resemble the original integral we started with. This is the hallmark of a recurring integral. So, we apply the integration by parts formula again to this new integral. Don't be afraid to repeat the process. That's the whole point. Step 4. Identify the cycle. This is where the magic happens. After the second application, you'll notice something remarkable. The original integral, the one we called I, has reappeared on the right-hand side of the equation. This confirms that we're dealing with a recurring integral and we're on the right track. Step 5. Algebraic resolution. Now, instead of continuing to integrate endlessly, we switch gears and use algebra. We move all the terms containing I, our original integral, to the left-hand side of the equation. This is a standard algebraic manipulation, and it's essential for breaking the cycle. Step 6. Solve for I. Finally, we solve for I algebraically. This usually involves factoring out I from the left-hand side and then dividing both sides of the equation by the number of times I appears as a factor. This will give us the value of the integral. And very importantly, don't forget to add the constant of integration, c, since we're dealing with an indefinite integral. So that's the overall strategy. We'll see it in action on the next slide with a detailed example. Remember, the key is to recognize the cycle, treat the integral as an algebraic variable, and use algebra to solve for it. This approach will allow us to evaluate integrals that would otherwise be impossible to solve using standard integration techniques. Conceptual analogy, the feedback loop. It starts by introducing the idea of a feedback loop in real-world systems. A feedback loop happens when whatever a process produces, its output, gets fed back into the process as a new input. Think about a thermostat controlling a heater. The thermostat measures the temperature. That's the output of the heating system. This temperature reading is then sent back to the thermostat. That's the input, which then decides whether to keep the heater on, off, or adjust the heat. It's a cycle, right? The output influences the input, which influences the output, and so on. Now the slide draws a parallel to cyclic integration. In our case, when we apply integration by parts, the output of that process isn't a nice, neat number, but rather the original integral itself. So, just like the thermostat, we're getting something back that looks very familiar. This means we haven't actually solved the integral in the traditional sense. We haven't reached a final destination. Instead, we've created a mathematical loop. We keep going around in circles if we just keep applying integration by parts. But, and this is key, we don't need to keep integrating. Remember, we treat the integral as an algebraic variable, I. That's how we break this cycle. We use algebra, adding, subtracting, and solving equations, to get rid of the loop and find the value of I, which represents our integral. This slide is about building intuition. It's about understanding that recurring integrals aren't about failing to integrate, but about encountering a situation where the integration process itself creates a loop, and algebra is the tool to resolve it. We'll see this in action with a detailed example on the next slide, so keep this analogy in mind as we work through it. Okay, so let's move on to slide 4. This slide isn't about doing any new math, but about helping you understand why we do what we do with these recurring integrals. We've already seen how, after applying integration by parts once or twice, we end up back where we started, with the original integral reappearing. This slide uses an analogy to explain this phenomenon. Detailed example. Okay, let's work through a detailed example to solidify our understanding of recurring integrals. As we discussed on the previous slides, these integrals require a slightly different approach than standard integration by parts. Problem: we want to evaluate the integral of e to the power of x times sine x, with respect to x. Step 1. Assign the integral to I. This is the first key step. We're going to treat the entire integral as a single variable. So, we let I equal the integral of e to the power of x times sine x. With respect to x, this just simplifies the notation and allows us to manipulate the integral algebraically. Step 2. First application of integration by parts. Now, we apply the integration by parts formula. Remember the formula is integral of u times v with respect to x equals u times the integral of v with respect to x, minus the integral of u prime times the integral of v with respect to x. We need to choose which function will be u and which will be v. A good strategy, and one we'll consistently use in these problems, is to let the trigonometric function be u and the exponential function be v. So we choose u to be sine x and v to be e to the power of x. Applying the formula, we get I equals sine x times the integral of e to the power of x with respect to x, minus the integral of the derivative of sine x times the integral of e to the power of x with respect to x. The integral of e to the power of x is simply e to the power of x. The derivative of sine x is cosine x, so this simplifies to I equals sine x times e to the power of x, minus the integral of cosine x times e to the power of x with respect to x. We can write this as I equals e to the power of x times sine x, minus the integral of e to the power of x times cosine x with respect to x. Step 3. Second application of integration by parts. Notice that we now have a new integral, the integral of e to the power of x times cosine x. This looks similar to our original integral, which is a key indicator that we're on the right track. We need to apply integration by parts again. This time, we're integrating e to the power of x times cosine x again. We'll choose the trigonometric function, cosine x, as our u and the exponential function, e to the power of x. As our v. Applying the integration by parts formula once more, we get the integral of e to the power of x times cosine x equals cosine x times the integral of e to the power of x, minus the integral of the derivative of cosine x times the integral of e to the power of x. The integral of e to the power of x is, again, e to the power of x. The derivative of cosine x is negative sine x, so this becomes the integral of e to the power of x times cosine x equals cosine x times e to the power of x, minus the integral of negative sine x times e to the power of x, which simplifies to e to the power of x times cosine x, plus the integral of e to the power of x times sine x. Step 4. Substitute the result back into the equation for I. Now, we substitute this result back into our equation from step 2. Remember, we had I equals e to the power of x times sine x, minus the integral of e to the power of x times cosine x. We've now found that the integral of e to the power of x times cosine x is equal to e to the power of x times cosine x, plus the integral of e to the power of x times sine x. Substituting, we get I equals e to the power of x times sine x, minus the quantity e to the power of x times cosine x, plus the integral of e to the power of x times sine x. Step 5. Identify the recurring integral. Look closely, we've come full circle. The integral of e to the power of x times sine x is our original integral I, so we can rewrite the equation as I equals e to the power of x times sine x, minus e to the power of x times cosine x, minus I. Step 6. Solve for I algebraically. Now, we treat this as a simple algebraic equation. We want to isolate I. Add I to both sides of the equation, which gives us 2i equals e to the power of x times sine x, minus e to the power of x times cosine x. Finally, divide both sides by 2 to solve for I. I equals e to the power of x with the quantity sine x minus cosine x, all divided by 2. Final answer. Therefore, the integral of e to the power of x times sine x with respect to x is equal to e to the power of x with the quantity sine x minus cosine x, all divided by 2, plus the constant of integration, c, and that's how we solve a recurring integral. Remember, the key is to recognize the cycle, treat the integral as an algebraic variable, and then solve for it. We'll discuss common mistakes to avoid on the next slide. Common mistakes to avoid. Okay, let's move on to slide 6. This slide highlights some common pitfalls students often encounter when tackling recurring integrals, so pay close attention. 1. Inconsistent selection of functions. A very frequent mistake is changing which function you designate as f of x, and which is g of x, when you perform the second integration by parts. Remember, in the example we just worked through, integrating e to the power of x times sine of x, we strategically chose sine of x as our f of x, and e to the power of x as our g of x. It's crucial that you maintain this choice in the second application of integration by parts. If you switch them, meaning you suddenly treat e to the power of x as f of x, you'll essentially reverse the effect of your first integration by parts. This will lead you to an equation where the integral I simply equals I, which, as you can imagine, doesn't get you any closer to a solution. It's like running in place. 2. Sign errors. This one is a classic. Be extremely careful with your signs when differentiate sine of x and cosine of x. It's easy to slip up. Remember that the derivative of cosine of x with respect to x is negative sine of x. A missed minus sign can be disastrous. Instead of getting a 2i when you rearrange the equation, you'll end up with I minus I, which equals 0, and that will completely derail your attempt to solve for I. Double-check those derivatives. 3. Forgetting the constant c. This is a fundamental rule of indefinite integration, and it's easy to overlook in the excitement of solving a complex problem. Since we are finding an indefinite integral, meaning we're finding the family of functions whose derivative is the integrand. Always remember to add the constant of integration, denoted by c, to your final answer. It represents an arbitrary constant and is essential for a complete and correct solution. So, keep these 3 points in mind as you practice recurring integrals. Avoiding these common mistakes will significantly improve your success rate. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire section. Key takeaways. Okay, let's recap everything we've learned about recurring integrals with these key takeaways. First, the definition. Recurring integrals are integrals where, as we discussed earlier, when you apply integration by parts $, and sometimes you need to do it more than once, the original integral you started with actually reappears on the right-hand side of your equation. Remember, this isn't a typical situation where integration simplifies things. It creates a cycle. Next, typical functions. These recurring integrals most commonly show up when you're integrating a product of an exponential function. That's e raised to the power of x, where a is a constant, and a trigonometric function, like sine of bx or cosine of bx, where b is also a constant. So, keep an eye out for integrals that look like that. Now, the I method. This is the technique we practiced. The most efficient way to tackle these is to temporarily replace the entire integral with a variable, usually I. This turns the integration problem into an algebraic equation that we can then manipulate and solve for I. It might seem a bit strange at first, but it really helps break the cycle. Finally, consistency. This is crucial and a common mistake students make. When you're applying integration by parts, remember how we chose which function to call u and which to call v? You must maintain the same priority, meaning the same function as u, across all steps of the process. If you switch which function you choose as u in the second application of integration by parts, you'll just end up going in circles and won't be able to solve for I. So, to summarize, remember the definition, recognize the typical functions, utilize the I method, and above all, be consistent with your choice of u and v when applying integration by parts. This will set you up for success when dealing with these types of integrals.